So I'm going to talk about the Phish-Market protocol, which is a cryptographic protocol. This is joint work with Tyler Moore. So before I start talking about the protocol, I want to give it a little bit of context. So this work is sort of part of research into modern cryptography, and I want to give a little bit of an idea what modern cryptography is about. So there are basically, say, two types of things that cryptography can help us do. So one type of thing is when we have a task that we want to perform with another party, and there's an adversary that's trying to prevent us from doing so. So for instance, if we want to send a message secretly to somebody else, and an adversary wants to listen in or eavesdrop on the messages. So encryption is a cryptographic solution to this problem. It's a way to prevent adversaries from listening in. And then we have similar problems where we want to send messages, but the adversary wants to change the messages en route. So authentication is a solution to this. Or we might want to identify ourselves to some other party, and the adversary wants to fraudulently pretend to be somebody else. Again, this is something that has a cryptographic solution. The other type of cryptographic problems are basically cooperation tasks, where instead of having two people who trust each other and are trying to do something together and a third person who's trying to interfere, we have several parties, none of which trust each other, but they're still trying to cooperate to do something together. So the first type of task is what we might call traditional cryptography. So this has been studied for maybe thousands of years. And the second type of task is something that's much newer. This is sort of in the realm of modern cryptography, and this is the type of thing I'm going to talk about today. So what are examples of cooperation tasks? So I think one of the best examples is elections, right? In an election, think of just a regular election. We have many parties. None of the parties really trust each other, but they still all have to cooperate and get a result that they all agree on. So this is one example of a cooperation task. We have, when we look at the context of the internet, we have a lot of other examples. So if we want to have an auction over the internet, but we don't have any trusted auctioneer, everybody wants to agree finally who gets the item that's being auctioned, but there's no single person we can trust. Everybody distrusts everybody else. And we have things like online poker, right? We want to play a game together, so we do want to cooperate, but nobody trusts the other person to shuffle correctly or not to cheat. So we have to have some way of enforcing this even without trust. So one thing to notice is that if we had a completely trusted third party, all these tasks would be really easy. So for instance, for voting, we could just tell this trusted party our votes. Everybody would just whisper in their ear who they're voting for. The trusted party would count all the votes and announce the result. And as long as we really trust this trusted party, then this is completely secure. And one of the really amazing results of modern cryptography is that anything we can do with a trusted party, we can actually do without a trusted party using a cryptographic protocol instead. So this is something called secure computation. And in theory, we can do this for anything. So OK, we have all these tasks, and the task I'm going to talk about today is another example of a cooperation task. It seems everything's solved, right? What else do we have to do? But it turns out that while it's true in theory that everything can be solved, in practice, it's not so easy. And the reason is that all these generic solutions are very inefficient. So they're inefficient in many different ways. So for instance, the computation required to do anything but simple addition with maybe multiplication is already very, very large. And for most tasks, it's infeasible. We have other problems as well. We have interaction problems. So for some of these tasks, the general solutions require everyone to interact with everybody else all the time. Things like voting, this is obviously something we don't want. We want voters to vote and go home and not continue with the protocol to do the counting as well. So this talk and a lot of my work in general is trying to find practical solutions to problems that cryptography can help us with that are efficient in practice. So what am I going to talk about today? So first I'll give I'll describe the problem, the phishing takedown problem. and how it fits into this cooperation framework. Then I'll describe a little bit why it's difficult to solve naively, what makes it actually an interesting problem. And then I'll describe our solution, the Phish-Market protocol. And the idea is to describe it using sort of intuitive concepts rather than math, although maybe I will have a slide of math for people who want it. And finally, I'll talk a little bit about our implementation, and if I have time, about an outgrowth of the implementation, the Qilin project, which is a Java SDK for writing cryptographic protocols. OK, so what is our motivation? So phishing, in general, is when criminals pretend to be, set up fake websites that pretend to be banks. So here I'm talking about banks. There are many phishing for other institutions as well, but I'm just going to say bank because it's easiest here. And then they set up a site, say this is a site that looks like Bank of America, but it actually is a completely different site set up by a phisher. And then users are tricked into entering their passwords. And once the phishers get their passwords, they can do various bad things with them. So the way this is often, the way that these sites often get the users is they send out spam with links. Your bank account has something wrong. Click here to fix it, and it brings them to a site that looks like their bank but isn't. So this is obviously a big problem for banks. And the way they combat it is they hire takedown companies. So what these takedown companies do is they look through the internet for phishing sites. And then through various means, they take them down. So they have relationships with ISPs and registrars, and they have many lawyers speaking many languages, and they can take them down pretty fast. But what I'm going to concentrate on now is how they get these URLs. So they get them in many different ways. So there are some public sources, like the anti-phishing working group maintains a list of URLs that people submit to them. And they also each have their own proprietary sources. For instance, they keep spam traps. They have servers whose only purpose is to collect spam and harvest the links and find phishing URLs this way. And they consider these their list of URLs a competitive advantage. So these companies are each hired. Usually, each bank hires one company. And so the companies compete between themselves on getting hired. And they consider this, the better lists, to be an advantage in getting hired. So they're competing for banks. But because they're only hired by a subset of the banks, they don't bother to take down sites for banks that didn't hire them. So what happens is you have many takedown companies. Each of them has this partial view of the world of phishing websites. And often you have some websites that are known to company A, even though the actual bank that is interested in them is a client of company B. So Moore and Clayton managed to get actual phishing URL feeds from 2 of these companies and did an empirical study, and they compared how many sites were known to one but should have been known to the other, and vice versa. And also, they estimated how much the banks were losing because the sites that weren't known to the proper takedown company weren't being taken down fast enough. And it turns out that just for these 2 companies whose data they got, the estimation was something like $330 million a year. So this is a very bad problem for the banks. So our proposal was to create basically an incentive to share. So the companies don't want to just give each other the URL information because they consider it a competitive advantage, because they want to keep various things secret. So our idea was maybe we can create a market where they get compensated for their URLs. Of course, as we said, they aren't willing to just tell each other the URLs because they're trying to keep things private. So we have to take into account the fact that they're competing. So let me introduce Sally and Bob. Sally is the seller. So we're going to now describe a mechanism for companies to basically sell each other URLs and keep private information they want to keep private. So standing in for the company who's selling the URL is Sally, and the company who's buying the URL is Bob. So in practice, we'd expect maybe the companies to be both sellers and buyers, but our protocol is one way. So our protocol lets one company sell something to the other company. We can run the protocol in the opposite direction as well if we want to have it bidirectional. OK, so what are the challenges we're trying to meet with this protocol? So first, Sally doesn't want Bob to learn anything except the URLs for his clients, because otherwise she's not going to be compensated fairly. He only wants to pay for those. On the other hand, Bob isn't willing to reveal to Sally his client list. So Sally shouldn't learn anything about Bob's clients. And of course, Sally requires Bob to pay for every new URL he learns. But Bob already has other sources for URLs. Right? He has public sources. He has his own proprietary sources. So obviously, he doesn't want to pay for URLs he already knew in advance. And finally, the whole point of this protocol is to get phishing websites down faster. And so we don't want this to take, say, a month to exchange a URL, because by that time, it's pointless. So we want everything to be efficient and fast. OK, so the first thing to notice is, again, if we had this trusted angel, then it would be easy. How would we do it with a trusted third party? So Sally tells the angel all of her phishing URLs, so everything she learned. Bob gives the angel his list of client banks and everything he knew previously. And of course, they're both trusting the angel not to tell each other these things. And then the angel tells Bob only the new and relevant URLs that he should be learning. And he tells Sally the number of URLs that she sold to Bob. So now Bob can just pay Sally according to this number. And because they both trust this angel, then they know that their private information remains private. The only thing Sally learned is how many URLs in total were sold. So she doesn't know which specific URLs were sold. And therefore, she can't learn too much about Bob's clients. Yes? That's right. Yes. Yes. So the claim is not that you learn nothing, because just knowing, say, if all the phishing URLs were for the same bank, then obviously we learned if that bank was a client or not. But we learn nothing beyond this number. And somehow it seems like we have to learn at least this much because they're going to be paid. Yes?
In a sense, I mean, not all URLs are equal. And when I buy a URL, how do I know that it is actually a relevant entry and not just some, so the verification of the information should also be important.
Right. OK. So that's a good question. So the question was, when I buy a URL, how do I know that I'm getting a good URL? Maybe Sally just makes up URLs and sends them to the angel, and then the angel sees them as new URLs that Bob doesn't know. So it's a good question. It's not something that we deal with the protocol. The idea here is that this is sort of a low-value protocol. So if after a month Bob sees that he gets trash URLs, then he's not going to be willing to pay much next month, or maybe he's going to stop doing business. So the basic idea is that URLs are not more or less valuable usually. If you have a URL that you didn't know and it actually is a phishing site, then you don't have any way to value it differently than other URLs, so they're all basically the same value. And if it's just trash, then you know somebody's misbehaving, and so you'll stop doing business with them later. So that's true. And again, our protocol is not going to fix any problem that this protocol with an angel is vulnerable to. So we're only going to do a little worse than this angel. But our hope is that this type of protocol is good enough, that companies will be willing to share information if they have the guarantees that this protocol gives them. OK, and of course, we want to do this without an angel. And the idea is that we're going to replace this angel with our cryptographic protocol. So what are the basic ideas behind this protocol? The idea is that we're going to do this transaction by transaction. So each URL is going to be a separate transaction. And we're going to pay for a transaction not with real money, but with encrypted coins. And the idea is that Sally won't be able to tell, Sally is the seller, she won't be able to tell whether Bob is paying with a real coin or a fake counterfeit coin until the end of the month. At the end of the month, she's going to know how many real coins he paid. So for a specific transaction, she's not going to be able to tell whether Bob actually bought the URL or not. But at the end of the month, she's going to be convinced that this is really the number of URLs that Bob bought. And we're going to make a few relaxations compared to this ideal world where we have an angel in order to make the protocol more efficient. So one thing we didn't have in this real world, in the ideal world, is that there Bob only learns the new URLs and that's it. And in our protocol, Bob is going to learn a little bit more about every URL, even though he's not going to be buying. He's going to learn which bank they belong to. So we call this a tag. Each URL is tagged with the bank that it belongs to. So Sally is going to say, I have a URL for Bank of America, and Bob is going to learn that she has a URL for Bank of America, even if he doesn't want to buy this URL. So this is one relaxation. And the other is that in this ideal world, Bob didn't learn anything about how many URLs that he already knew, Sally also already knew. And in our protocol, he's going to get this information as well. But this is going to make the protocol a lot more efficient. This is why we're willing to make this sacrifice. So how does a transaction look like? So it's basically in 4 stages. So first, the seller offers the URL to the buyer. So Sally tells Bob, I have a URL for bank X. And then Bob decides whether to take it or not using a cryptographic building block called Oblivious Transfer. Next, Bob sends his encrypted payment. So again, this uses a cryptographic building block called homomorphic commitment. Don't worry if you don't know what these are. I'm going to explain all of them in a moment. And then we said these are sort of encrypted coins. So Sally has no idea whether they're real or not. But Bob still has to show somehow that he's doing the right thing, that he's actually paying when he should be. So he makes 2 types of proofs. First, he proves that the payment is good. So in our case, a good payment would be an encryption of, I owe you $1, say. And next, he also proves that he knew the URL in advance. That is, this is one of the URLs he already knew, and so he shouldn't be paying for it. And both these proofs use a building block called a zero-knowledge proof, which means that the only thing Sally learns about this is the statement that Bob paid something good or that Bob already knew the URL. Of course, if Bob's side of the protocol always looks like this. So Sally always sees the same thing. She always sees this oblivious transfer, the payment, and then 2 proofs. But something must be wrong here because it can't be that Bob always pays or that Bob always knew the URL in advance. And this is the main trick that makes the protocol work, and I'll show how we get around that. So before I actually get to the protocol, I'm going to describe what are the building blocks we use, these 4 different building blocks. So the first is commitment schemes. What is a commitment? So you can think of a commitment to a value, so this is the value here, this document, as putting it in a locked chest and sending the chest to Sally. So the idea is that it's hiding, so Sally can't tell by looking at the chest what's inside it. And you can think of this also as encryption. So if I give you an encrypted value, it's hiding. You can't tell by looking at this encrypted value what's inside. But later, Bob can give Sally the key, and then she can open it. Whoops. And the idea is that the commitment is binding. So once I've given Sally the chest, I can't change what's inside. I'm committed to the value. So those are the 2 properties commitments have. And basically, we use commitments for 2 things in this protocol. First, Bob is going to commit in advance to all the URLs he already knows so that he'll later be able to prove that he knew something before Sally gave it to him. And also, he's going to use these commitments as the encrypted coins. So payment is actually a commitment to pay. Next, we have our second building block, zero-knowledge equivalence proof. So this is zero knowledge is something very general. We can do a lot of things with it. I'm going to only talk about this specific thing we need here, which is we want to be able to show that two commitments are commitments to the same value without revealing anything else, and in particular, without revealing what the value is. And so I'm going to use a physical metaphor for this. So pretend the value is actually the weight inside. Right? So looking at the chest, we can't tell what the weight is. But if we had a scale, then we could put these two chests on the scale, and as long as it's a balanced scale, or in this case it's a balance, so we can't tell what the weight is, but we can tell that they're the same. So there's a mathematical equivalent of this for commitments, but we're going to ignore how the math actually works for now and say that we have this type of primitive, that we can show you that these two commitments are to the same value and not reveal the value. And where do we use this? So we use this to show that the payment is good. So we said a payment is a commitment. So a commitment to 1 says, I'm going to pay you $1. And a commitment to 0 is the counterfeit coin, which is, I'm not going to pay anything for this URL. So when we want to say that the payment is good, we're going to prove in zero knowledge that this commitment is actually equal to a commitment to the value 1. So if they're commitments to the same value, then you know that this is a good payment. And of course, we also need this zero knowledge proof to show that Bob already knew in advance the URL. So we're going to say this URL that I just got from Sally is the same as one of these URLs I committed to in advance, and so I already knew it. So this is how we show that Bob already knew something in advance. But of course, we said that it's not always true that Bob is paying for the URL, and it's not always true that he knew in advance what the URL was. And so we add an extra twist to these zero knowledge proofs. We have a zero knowledge proofs of equivalence with a trapdoor. So what is a trapdoor? So you can think of it as this secret key that lets Bob fake the proof. So if Bob sticks this key in the balance, then it's now locked. And so it doesn't matter what you put on it, it'll always appear to be equivalent. And the point is that even though in the picture Sally can see there's a key in there, in real life, in the mathematical equivalent of this, Sally won't be able to tell whether this is a fake proof using a key or a real proof without the key. And this is going to be sort of the heart of the idea. Sally won't be able to tell when Bob is cheating, but we're going to limit the number of keys Bob has, and so he won't be able to cheat all the time, and this will ensure that he pays when he should be paying. Okay, we need only 2 more building blocks before we actually get to the protocol. So the first is Oblivious Transfer. So this is how Bob can learn the URL or not learn the URL, depending on whether he's interested, without Sally knowing. So you can think of this as Sally putting a document, say this is the URL, in one chest. And in our case, she's going to put a key in the second chest. And then she locks the chests and sends both keys to Bob. So Bob knows that this is the key to the URL, and this is the key to a second proof key. But Bob is only going to get to choose one. So he chooses the key he wants, and he sends the key back to Sally, the other key back to Sally, and she discards it. And the point is, again, in this physical analog, you might think that Sally can tell, which key is which. In the mathematical equivalent, they're indistinguishable. So Sally can be certain that Bob only has a single key, but she can't tell which key Bob chose. This is the oblivious part of the oblivious transfer. And now when Bob gets these chests, he can only open one of them. So in this case, say he chose to open the URL, and then he can no longer open the other one. OK, and our final building block is what lets us sum up the things at the end of the month. It's homomorphic addition. So what we said earlier was a general commitment, what we described. What we're going to do is use a commitment with an additional property called homomorphism. And the idea is that we can add commitments without opening them. So here we have say, a coin, and this is the commitment to the coin, so it's a payment commitment. And we're using envelopes instead of chests, just so it'll fit in the piggy bank and it'll be nice. So the idea is that we can put these commitments in envelopes. Sally can't tell what's inside the envelope. We put them all in this piggy bank. But at the end of the month, we can see how much it weighs, basically get the sum of all the commitments without revealing which commitments contributed to the sum. So Sally won't be able to tell which specific transactions were ones in which Bob bought a URL, but you'll be able to tell exactly how many he bought at the end of the month. OK, so those were the building blocks. Now I'll describe the protocol itself. So this is sort of a high-level summary. So first, we said Bob commits to all the previously known URLs. So he sends commitments to everything he already knows. Now Sally sends a few things to Bob. So she sends the tag. The tag is what we said, the name of the bank. So this is a URL for Bank of America. Oops. She sends a commitment to the URL. So we'll see why this is needed later. But from the commitment, remember, it's hiding, so Bob doesn't learn anything. And she sends already a single zero-knowledge proof key. This is the key that's used in the balance. So already Bob can fake a single proof. Now, Bob and Sally together perform this protocol called Oblivious Transfer, what we saw with these two chests, where Bob gets to choose whether he wants the URL, this is what's in one chest, or he wants a second proof key. So remember, he already had one in the beginning. He can get another if he's willing to give up learning the URL. And so he gets one or the other depending on what he chose. And Sally doesn't know what he chose. And then Bob sends his payment. So this is an encrypted payment. It's a commitment to the payment. And he also sends a commitment to a URL, which is one of the URLs he previously knew. And now they have these two proofs. So first, Bob is going to prove in zero knowledge that E, this is the commitment to the payment, is actually a commitment to 1. So this is a real payment. And next, he's going to prove that U, this commitment to the URL, is equivalent to the commitment that Sally sent over here. This is why we needed Sally to send a commitment to a URL here. Obviously, Bob can't prove he knew the URL before by just saying the URL, because this would tell Sally that he learned the URL. So this is why we use this sort of extra layer of commitment. Sally sends a commitment to URL, and he sends a commitment. And he proves that these two commitments are the same without ever revealing what's inside. And then we have a third proof, which is that U is in this set of previously known URLs. So for now, let's just pretend that U just is one of those URLs, and you can just see. So we'll ignore this proof for a second. OK, so let's see basically how this protocol works. So as you said, in the beginning, Bob has a single proof key. And suppose he didn't want the URL. So he looked at the tag. Bank of America isn't one of his clients, so he doesn't want to learn the URL. So in the OT, he decides to learn the second proof key. So now he has two proof keys. OK, he has two proof keys. Means he can send a bad payment, a payment to 0. But instead of really proving that the payment was good, he uses a proof key. Sorry. He also can send a fake, he has to send a fake previously known URL because he doesn't even know what the URL is. So he doesn't know whether he knew it before or not. So he has to send something that is different here. And then he can use a proof key here and a proof key here. So both these proofs are fake, although to Sally they look real. And in this case, Bob doesn't have to pay. So Bob is happy. If he didn't learn the URL, he doesn't have to pay. Yes?
How does he know if he wants the URL if he only lets the tag and not the URL?
So he knows if he wants the URL just based on what bank it is. If it's a client of his, he wants it. If not, he doesn't. OK, so we'll get to a second. So the first question he asks is he interested at all? And we'll get in a second to what happens if he's interested, but he already knows it. So suppose he is interested. Bank of America is one of his clients. And so he gets the URL. He still has only one proof key. And suppose now that this is a URL that he didn't know in advance. So this is the case where he should actually be forced to pay. So he didn't know it in advance, so obviously he can't send here a URL that is equivalent to this one, because he won't be able to prove that he knew it in advance. So this proof is going to have to be faked, which means he's going to have to waste his proof key on this proof. But that means that he has to prove this one. He has to use a real proof here. And so he has to actually pay in this case. So Sally is happy here, because if Bob learned a new URL and he didn't know it already, he's going to be forced to pay. OK, and then this is the case that you were talking about. What happens if he wanted the URL, but it turns out that he did already know the URL? Well, in this case, he can choose the URL that is equivalent to the URL that Sally sent him. And so he can use a real proof here. He doesn't need to fake it. But that means he can choose a fake payment and then use his proof key here. So again, if Bob already knew the URL, he's not going to be forced to pay. So this is basically the whole protocol in a nutshell. So what do we guarantee about this protocol? So we make some formal security guarantees. And the first question that many people ask who aren't actual cryptographers, and even some who are, is why do we even care about formal security guarantees? Right? We can sort of see it works. It looks good. Why do we need anything more than that? So basically, what I claim is that for protocols where security and privacy is important, there's basically no other way to be certain that your protocol is good. Why? So if you think of an algorithm, say a sorting algorithm, if it doesn't work, you try to sort things and you see that they aren't sorted correctly, or that it doesn't terminate. Something goes wrong and you can tell. If you have a protocol like this, but it actually reveals to Sally all of Bob's client list, then you're not going to see that something went wrong, because it's going to work correctly. Bob is going to see everything completely fine, but Sally is going to learn something that she shouldn't. And so the only way we can get some confidence that Sally actually isn't learning anything is through some other mechanism. And this is what these formal security guarantees, these proofs, give us. And of course, when we say a formal proof of security, we're not proving that this protocol is secure. There's no such thing. What we are proving is that given that a few specific assumptions are true about how we run the protocol or about some mathematical assumptions, then the protocol is secure. OK, so why does this help us? The difference is, so maybe we can, we have this protocol and we try to attack it in many different ways and we think it's secure. Right? This is often what happens for encryption schemes. But what this means is, if we have many types of protocols, there are going to be very few people who are trying to actually attack this entire protocol. Right? Very few people are going to put a lot of effort into cracking this Phish-Market scheme, compared to, say, factoring numbers or breaking RSA. And so what these formal guarantees give us is a reliance on small assumptions that are hopefully generic. So instead of saying, as our assumption is this protocol is secure, which might be true, we give as an assumption factoring is hard. And this is an assumption that many, many people have looked at. And we know that many more people have tried to do it and failed than have tried to look at this protocol and failed to break it. So it gives us a lot more confidence. OK, so having hopefully convinced you that formal security guarantees are important, what do we actually guarantee about this protocol? So we make two different guarantees for the seller and the buyer for technical reasons. So for the seller, we're basically saying that this is equivalent to our ideal world where we had this angel. So anything that the seller can learn in this protocol, the seller could also learn in the ideal world with the angel. For the buyer, we make a slightly different guarantee. So it's not equivalent to an ideal world. What we say for the buyer is that the seller doesn't learn anything about the buyer's secrets from a single transaction, anything at all. And from the entire protocol, the seller learns nothing except what she knows from the number of URLs sold. So those are the two types of guarantees we make. OK, and now for a few loose ends. So I said before we were ignoring this proof number 3. Why did we have a separate proof that the URL is one of the URLs I previously knew, or that Bob previously knew? The reason is that Bob may know 10,000 URLs. So if for every transaction he has to send 10,000 commitments to Sally, this is going to be a very inefficient protocol. So instead of sending 10,000 commitments, we're going to use something called a Merkle tree that lets Bob send a single commitment that's basically a commitment to 10,000 URLs at once. And the way this works is this looks like a tree where each node of the tree is a commitment. And so the leaves are the actual URLs. And the internal nodes are each commitments to the children. So if I want to show that I knew a URL, all I have to send is this root of the tree. This is a single commitment. And then to prove that something was in the tree, I show you that this path in the tree. So I open this commitment and so on, just up to the root. And because of the way commitments work, I can't basically prove anything about a leaf that I didn't put in the tree originally. So this makes our proof a lot more efficient, but it's not zero knowledge. So because we learn something about this tree every time we use it, and this is why we sort of separate into two parts. We have a zero knowledge proof, and we prove something about a commitment to URL rather than to a URL. And the leaves here are not going to be actual URLs. They're going to be commitments to URLs. And in order to prevent learning too much about the structure of the tree, we're going to have leaves that are fake leaves as well. So remember, in some cases, I have to give a URL. If, for instance, I didn't learn the URL, I still have to show you that I already knew something in advance. So I'm going to have to give you a real leaf of this tree. But in order for this not to reveal anything about other URLs I know, then I'm going to just put in fake leaves so I can just give a fake leaf when I have to. So I'm not going to get too much into the details of this. We still have some time, right? So I want to, this is the only slide with actual math on it. So I want to describe a little bit about how we do this equivalence proof with a trapdoor. So it's not too much math, basically only addition and subtraction. We said we have commitments that are homomorphic. So what we mean by homomorphic is that if we multiply two commitments, we get a commitment to the sum. And if we divide two commitments, we get a commitment to the difference. So this is the math you need to remember for this. And so suppose we want to prove that two commitments are equivalent. So we want to say that x and y are actually the same value. So if these commitments are homomorphic, it's actually enough to prove that the quotient is actually a commitment to 0. Because if they were the same value, when we divide them, we get a commitment to x minus y, and that should be 0. So now I'm going to show how you can prove that a commitment is actually a commitment to 0 without ever opening the commitment. So this is sort of a standard protocol. It works in 3 stages. So we have a prover and a verifier. So the prover here is going to be Bob, and the verifier is going to be Sally. So say Bob is proving that a commitment is actually a commitment to 1. So the prover first chooses a random value b and commits to b. So he sends a commitment to b and also b itself. But this isn't an opening of the commitment. This is just a claim that this commitment actually opens to b. Next, the verifier picks another random value, say a, and sends a to the prover. And now the prover actually opens a commitment, but the prover opens the commitment to ax plus b. So this is a commitment that can be constructed using the homomorphic property by taking this commitment c of x that we're trying to prove something about, raising it to the 8th power. So this is like multiplying a times. So basically, because it's homomorphic, it means we get a commitment to a times x. And we multiply it by c of b, by commitment to b. And again, because it's homomorphic, it's like adding b. So this is something that the verifier can do as well. This is something public, so we get this commitment to ax plus b, and the prover just opens it. And of course, if x was 0, then this should always be b, exactly. Right, and we just want to note that all the arithmetic here is modular, so it cycles around. And the main idea of the proof is that if I didn't know, if x is not 0 and I didn't know a in advance, then with high probability, I can't find no matter what I said here. So potentially the prover can lie and say something else. He can give a commitment to B and say this is actually a commitment to B prime. But no matter what he chose here, if A was random and he didn't know it in advance, this is not going to be B with very high probability. So this is why this is a convincing proof that actually this is a commitment to 0. But why is it 0 knowledge? Why doesn't it reveal anything else? So the idea here is that we can show that the prover can cheat if only he knew A in advance. So if instead of doing it in this order, first the prover learned A, and then he could commit, then he could simply compute AX plus B and claim that this was what's inside this commitment. And now the verifier, everything will look completely the same, and we'll get a value that looks correct here. OK, so this was the math slide. So that was how to do a regular equivalence proof. But we wanted an equivalence proof with a trapdoor. So how do we add a trapdoor? So the idea is that this zero-knowledge proof is a type of zero-knowledge protocol called the sigma protocol. And sigma protocols are exactly these protocols that have these 3 stages, where the prover commits something, the verifier sends a completely random challenge, and then the prover opens the commitment, or a commitment that's related. And for all these sigma protocols, there's a generic way to add a trapdoor. So how do we add a trapdoor? We keep the same structure, except instead of having the verifier send a random challenge, they're going to together do some protocol for coin flipping, which selects this random challenge together. So far, this actually is also a zero-knowledge proof. It looks exactly the same. But if we had a coin flipping protocol with a trapdoor, where by trapdoor I mean the prover could basically fix in advance what the result of the coin flipping protocol is going to be, then we already showed that we can fake the proof here. So this gives us a trapdoor. How do we get coin flipping with a trapdoor? So let's look at the Blum Coin-Flipping protocol. Again, it uses commitments. So here, Bob chooses a random number, commits to a number, sends Sally the key, so now he can't open it anymore. And Sally, of course, only sees the key. She doesn't know the value. And now Sally chooses a random value and sends it to Bob. And then Bob opens, sends the chest to Sally. She opens it, and the coin is the random value. So if Sally didn't know what Bob's coin was, then no matter how Bob fixes the coin, if she chooses a random value, this is going to be random. And in the same way, if Bob doesn't know what Sally is going to do, then no matter what he puts inside the coin, this is still going to be random. So none of them can cheat. This is a fair coin flipping protocol. But the point is that if Bob had this trapdoor key to the chest, so instead of being forced to commit to a value, he could change the value, then he could equivocate. He could open it to a different value. So then after seeing that Sally's value was 124, he could change his value to get whatever final coin result he wants. And this is basically what we do for trapdoor coin flipping. OK, that was everything I had to say about the protocol. We also actually implemented this protocol. So we used specific types of commitment and oblivious transfer that don't really matter. The point is that they're both based on a specific mathematical assumption called the hardness of discrete log. And this is something that's true in generic groups. And we have a few different implementations of the instantiations of these groups. So they work over elliptic curve groups and over modular arithmetic. And we implemented both cases. And we also tested the performance using the real data that Moore and Clayton received from these companies. So this is a graph showing the delay, the percentage of transactions that were delayed by this number of seconds. So per transaction, a single transaction basically is about 2.5 seconds, I think. This was on a fairly old computer. But because transactions get queued, then sometimes the actual delay can be a bit longer. The average delay that we measured for something like 2 weeks of data using sort of real-time simulation, and about 10,000 URLs was about 5 seconds, and even the worst case was only 35 seconds. So in terms of efficiency, this is completely practical for real-world use. When you think of the actual taking down of a website is something that's not on the order of seconds, but more of hours. So a delay of 35 seconds doesn't really matter. OK, so I've shown a practical solution for sharing data between competitors, which doesn't require any angels to actually implement. And what I haven't shown, but is true, is that this is also applicable to other types of data sharing problems that have similar constraints. So on one side, there are problems where we don't have to hide as much. So for instance, if we didn't have to hide the client list, then this protocol would be much, much simpler. We could cut out many parts of it. On the other hand, here we made some relaxations where we reveal information that we wouldn't have to reveal in the ideal world, such as the tags of the banks. And we can make the protocol a little more complex by adding some general techniques only for that and hide more information. So there are 2 directions we can go there. And finally, I want to talk a little bit about sort of more cryptographic protocols in general. So if we look around and see what kind of cryptographic protocols are actually used, we see there's a lot of traditional cryptography. So there's a lot of encryption. It's used everywhere. Signatures are also used basically everywhere. What we don't see is sort of these types of advanced cryptographic protocols. And I know of very, very few actual cases where they've been used. So I think there's, in Denmark, they've used the secure computation to hold auctions for contracts of sugar beets. And there are a few voting protocols that use more advanced protocols that have actually been used in practice. But apart from that, I really don't have any examples of real-world use of advanced cryptographic protocols. And on the other hand, it seems like there are a lot of cases where crypto could help us, where these problems that people actually need to solve, and it seems like cryptographic protocols are a really good fit. Why aren't they being used? So I have a few theories. One of them is that people who write these crypto protocols usually publish them in theory papers and theory conferences. And people who go to theory conferences and read theory papers aren't that interested in implementing stuff. The other is that when they do implement, they usually implement sort of one-off things. So they have a protocol, they implement just this protocol, and then it's very hard to take this and use it for anything else except this specific thing they were thinking of. And finally, we do have a lot of libraries for crypto. If you look around, there are various different commercial and open source libraries, but almost all of them are just completely focused on the traditional uses of encryption. So to give an example, El-Gamal encryption is a popular type of encryption, and it's in fact homomorphic. So it has the properties that we need, for instance, to use in this protocol. However, when we think of using it for actual encryption to transmit messages, the homomorphic property is bad, because it means that the cipher is vulnerable to an attack called the chosen ciphertext attack. So to prevent this, all these libraries usually wrap the encryption in a layer that makes it secure against chosen ciphertext attack, but then it completely hides this homomorphic property. So you can't use it for protocols in an easy way. So what I claim we need is standard libraries for cryptographic protocols that are aimed at actually building cryptographic protocols rather than using these traditional things. And this is where the Qilin project comes in. So basically, when we started implementing this Phish-Market protocol, I looked around for anything I could use to build this protocol or something similar, and couldn't find anything generic. And so I started writing a library. Qilin is a Chinese mythological beast, somewhere between a unicorn and a dragon and a giraffe or something like that. And the idea is that we wrote this library. It's a Java library for rapid prototyping. So the idea is it will be fast to write protocols using this library, and it's going to use concepts from the theory of crypto. So if you read a crypto paper, a theory paper that describes a new protocol, it's going to be fairly easy to see what you need to do when you're implementing it. And you won't have to translate this into specific things. They say commitment, and you need to know that you're looking for something called Pedersen. And so what we have currently implemented are all the building blocks that we needed to build the Phish-Market. So instead of Elgamal and Pedersen are encryption and types of commitments that we use. It's generic enough that we can instantiate basically over elliptic curves or over modular arithmetic without changing the code. So you can write your code using homomorphic encryption without even specifying what type of homomorphic encryption is going to be, and later plug in Elgamal over elliptic curves and without changing your code. And it has some other nice things like we said our zero knowledge protocols, for instance, the ones we described, they're all interactive. So we have this, we send something, the verifier sends something back, we send something there. There's a generic transformation from Sigma protocols to non-interactive protocols, which is called the Fiat-Shamir heuristic. So one of the things this library does is let you write a Sigma protocol in an interactive way, which is sort of easier to think about, and automatically transform it into a non-interactive version. And it's open source. You can get it online at Qilin Seeds Harvard EDU. You can also find a link on my homepage. And if anyone's interested in using or contributing to this, I'd be happy to talk to them. Any questions?
So, on the implementation side,
Yeah.
The difficulty of computation for a single case, is it one case to 35 seconds?
No. So a single case always takes 2.5 seconds, or at least on my computer. But the 35 seconds is if there's a long queue, and they come in faster than 2.5 seconds. Yeah.
So the protocol is between two parties.
Yes.
Does this mean that all of the anti-phishing companies are going to need bilateral agreements with every other company?
So
Or is there some way of sort of scaling this to many companies?
that's a good question. No. So it's a two-party protocol. It's not completely clear how you define this multi-party protocol, even in the ideal world. And we haven't thought of doing anything. But the bilateral agreements here aren't very complicated. So. Yeah, it's all online. So you have one company is the seller and one is the buyer, and you run the protocol in the opposite direction as well. So whenever you have a URL, you can also try to sell it.
Do you have an idea of what the actual volumes, that the companies would like to share with that they?
Yeah, so we did this on actual data. So I think for like the largest company had something like 10,000 URLs for a 2-week period. It's a fair number.
Somebody brought up a point that if you're the seller, based on the number of coins that may come up, you might be able to figure something out about who your buyer is and who the
Right.
coins are. We thought at all about, so when there's a buyer, just buy 3% of all URLs at random.
So we didn't analyze the actual information leakage. Even your countermeasure, I mean, if the seller is sort of malicious enough, then even that wouldn't work, because suppose a seller sends only URLs for bank A, right? Then I can tell if it's 3% or a lot above 3%, the buying rate. But part of the idea, this model isn't a completely malicious model. So we're basically assuming that there's some external thing that can be done. So for instance, one thing we don't protect in this protocol is if Bob decides not to pay up at the end of the month. Right? There's this commitment to payment, but Bob can decide not to pay. And there's no way to enforce this sort of inside the protocol. And so we're assuming there's an external framework, for instance, that it's a repeated game, so maybe you just won't play anymore if you cheated in one version. And, or what? Or you have a contract. For things like learning the client list, so here actually the fact that you get tags is helpful because you can tell whether you send all the tags for a specific, if you're acting very suspiciously, then you can see that something's going on. Whereas if you just see the tags that you bought, then you can't tell.
Getting agreement on, I guess, both parties, and in the case of this market, like all 12 parties would have to agree upon the set of tags for all.
So the tags are just the names of the banks. It's not.
But,
The tag isn't part of the protocol. So you can.
It's
It's true there is variation. Even in the list between different institutional companies, often they don't what they name same banks, especially when they're only concerned about applying to banks that are not being paid by us to throw everything.
yeah.
So that would
Fargo, but there may be Wells Fargo, blah blah blah.
yeah, that
Yeah.
would have to be.
You could already do that because each bank already has a unique number associated with it for the on your checks for the processing of payments. So if you want to set it
Yeah, that
up,
would be right.
Okay.
Right.
Yeah.
But that only works for U.S. banks.
so that only works for US banks. Yeah.
But all the companies in the U.S. based have foreign banks.
Yeah, and there are maybe other institutions.
What about just the URL being Phish? So what about just using the main URL being Phish? So
Oh, yeah.
Yeah, but that's harder.
There are lots of ways to do it. The problem, as you say, is just getting the different ways to coordinate on what they're going to do.
Yeah. It's right. It's not cryptographic.
Yeah.
It's just
Nitty-gritty.
Okay, so thank you.